Right, this is an exam question doing a calculation on Born-Haber cycles. So it's asking us to use the data in that table to calculate the enthalpy of lattice dissociation of potassium oxide. So the first thing we need to do is draw the Born-Haber cycle out and write all our figures in. So first thing I'm going to do is read that question properly. It says the enthalpy of lattice dissociation. We need to be careful that we're doing the correct lattice enthalpy because it can be the lattice enthalpy of formation or dissociation. So I'm going to draw at the bottom my ionic solid, which in this case is K2O. So in this case, they've given us the formula of the product. But if they just give us the name, then we need to be careful that we work out the formula correctly, using the idea that group 1's always +1, group 2's always +2, group 3's +3, etc. And the halogens in group 7 are always -1, group 6 is always -2, etc. So it's given us that. Remember, we need to put all the state symbols in, so it's an ionic compound, it's going to be a solid. So the first thing I'm going to do is draw in the enthalpy of lattice dissociation. So I'm going to draw this slightly higher up than I normally would. Because it's oxygen, we're going to have two electron affinities. We're going to have the first and second, so we then need to have some space down here. So lattice enthalpy starts with our gaseous ions, so I need 2K plus and they're gaseous, and I've got 1 oxygen and that's 2 minus. And it's lattice enthalpy of dissociation, so it needs to be going from the bottom to the top. So I need to label these, so lattice enthalpy of dissociation. And that's what I'm trying to work out, so there's no value for that one. Then on this side we have the enthalpy of formation, so that goes down. So enthalpy of formation and remember that goes from the elements in their standard state. So potassium's in group 1, it's a metal, so that's going to be 2 potassiums as a solid, and oxygen we should hopefully know is gas. So that's now oxygen is diatomic, so it's going to be half of an O2, and that's going to be a gas. And if I look in the table, the enthalpy of formation of potassium oxide is -362. Right, then we're going to do the atomization. So we're going to do the atomization of the potassium first. So that's going to potassium as a gas and half of the oxygen, so the oxygen gas is staying the same. Now, because we've got 2 potassiums, we need to times that by 2, so it's 2 times the atomization sorry, 2 times by the enthalpy of atomization of potassium. So again, if I look at my table, that's 2 times 90. Right, then this needs to be ionized. So it's going to go to 2K plus 2 electrons, and then the oxygen stays the same again. And because there's 2 potassium atoms being turned into 2 potassium ions, that's going to be 2 times the first ionization energy. Of potassium. And again, if I look in the table, that's 2 times 418. Right, so now, I'm sorry, I forgot my state symbol there. So now my potassium's exactly where it needs to be. I just need to turn my oxygen. So the first thing I need to do is the atomization of my oxygen. So this is my atomization of oxygen. And if I look in the table, that's plus 248. Now this is going to be a bit more complicated. Well, I've not written that at the top. So 2K plus is a gas, plus 2 electrons, plus O as the gas. So now I need to go from oxygen as a gaseous atom to O2 minus, and we need to do that stepwise. So I need to go to O minus first and then O2 minus. So the first electron affinity is always exothermic, and exothermic goes down, remember, on our cycles. But the second one is endothermic. So I need this to go here. So my K plus stays the same. I've got one electron left over, and I've got my O minus as a gas. So this coming down to here is my first electron affinity. And if I look in the table, that's minus 142. And then I've got my second electron affinity. Of oxygen. And if I look in the table, that's plus 844. So if you look at these arrows, you'll see any arrow that's going down, so these two are negative numbers, and any arrow going up is positive numbers, which is what we would expect. So that's my Born-Haber cycle complete. So the next step is to work out my calculation. So what I'm trying to work out is going from here, so this is the start, to here, which is the finish. So if I'm going from there to there, but I'm going in the other direction, so I'm going round there, what I need to remember is that if I go against an arrow, I need to take it away. And if I go in the same direction as an arrow, then I add it. So I can now write at the top here my lattice enthalpy equals. So I'm going to go minus my sorry, you can't see on that. So I'm going to go from here to there. So that's minus the minus 362. And then I'm going in the same direction as arrow, so it's 2 times the 90. So it's adding that one, so plus 2 times 90. And then I'm looking at this one, so that's I'm going in the same direction as the arrow, so it's plus 2 times 418. And then I'm adding, I'm going in that same direction as the arrow, so I'm adding 248. And then here I'm going in that same direction, so I'm adding, but I'm adding a minus, so it's adding 142. And then I'm going in the same direction as that second electron affinity, so I'm adding 844. Now you can go straight to typing in your calculator here, but I like to write it out properly because otherwise I tend to make a mistake. So I'll just turn that into, so that's plus, minus is plus, that's 362, plus 2 lots of 90, plus 2 lots of 418, plus 248, minus 142, plus 844. Okay, if I just stick that into my calculator. Okay, so that's 362 plus 2 lots of 90 is 180 plus 2 times 418 plus 248 minus 142 plus 844. And that gives me 2328. And we've got to remember to put our, so let's remove the calculator. We've got to remember to put our units on that. That's going to be in kilojoules per mole. So that's our answer for that question.